In this lesson, we're going to play around with our gradient descent algorithm a little bit, and we're going to see how it is affected by our initial guess, by our starting value. Also, we're going to be building on our Python programming skills by covering some of the more advanced features of functions in Python. The first thing we're going to do is we're going to generate a new cost function and kind of go into a second example. So I'm going to change this cell at the bottom here again to Markdown so that we have a nice clean section heading. And we're going to call it example 2 multiple minima versus initial guess and advanced functions. The cost function that we're going to be working with is going to look like this. It's going to be $2 g of x is equal to x to the power of 4 minus 4x squared plus 5 and then $2 at the end. So again, we're going to be using LaTeX Markdown to write our function in mathematical notation. So as we've talked about before, remember that LaTeX uses tags to mark text for special formatting. And there's two tags here, right? There's an opening tag of $2 and there is a closing tag of $2. Now let's get stuck into the Python code. So the first thing we're going to do is we're going to make some data. Now I'm going to create a variable called x_2, since this is going to be our second example. And again, we're going to be using NumPy's linspace to generate our values. So I'm going to have values starting at -2, going to 2, and I'm going to space them out with about 1,000 values. Now, as a challenge, can you write the g of x function and the derivative, the dg of x function, in Python? So remember, you're going to be writing two functions with the def keyword and applying that power rule that we covered in the previous lesson. I'll give you a few seconds to pause the video and write these two functions. Ready? Here's the solution. It's def keyword g of x colon return x 2 times symbols power of 4 minus 4 times x 2 times symbols 2 plus 5. So that's our first function. But the derivative of this function, applying the power rule, is going to be df dg of x colon, and then it's return 4 times x to the power of 3 minus 8 times x. So 4 gets multiplied by 2, becomes 8, and the constant drops out. And that's it. I'm going to hit Shift-Enter. And if you get this error that I've gotten, you got to scroll all the way up to where you're importing NumPy and just hit Shift-Enter on this cell again, because NP was not recognized by Python because I haven't come back to this notebook in a while. Now I can click back into this cell and hit Shift-Enter and it'll run just fine. Now it's time to plot the cost function for this example. I'm going to scroll back up for a second here, and I'm going to grab this cell here, and I'm going to copy it because we're going to be reusing some of this code. So I'm going to copy this cell, and I'm going to come here and go to Edit, Paste Cell above. But I'm going to have to make a couple of changes here. So first off, I'm going to change the x-axis to go from -2 to 2, and the y-axis to go from 0.5 to 5.5. And then I'm going to change the label here on the y-axis as well to g of x. And of course, on my plot, I'm going to take x_2 and g of x_2. And similarly, for my derivative, the y label is going to be dg of x And for my x-axis, I'm going to go from -2 to 2 as well. And for my y-axis, I'm going to go from -6 to 8. And when it comes to plotting, I'm going to plot x_2 and dg of x_2. I'm going to hit Shift-Enter, see what I get. Voila. So these two plots help us visualize our second example's cost function. So what can we observe here? What can we see? Well, there's a couple of things that are of note, right? So if we look at the chart on the left, we can see that there are two minima. There are two places where the cost is very low. One here and the other one here. Also, looking at the right-hand chart, we see that the derivative intersects the x-axis on 3 points, right? One here at x = 0, and one here. So there are 3 points when the slope is equal to 0. And those 3 points correspond to this minimum, but also this maximum here. Now, it's going to be very interesting how this affects our gradient descent algorithm. But before we start playing around with the starting values, we're going to make some modifications to our Python code, because this is a really, really good time to talk about some of the advanced features of functions in Python programming. Now, we've written our code already for the gradient descent algorithm, but what we're going to do is we're going to scroll up and we're going to take this cell and copy it. And then we're going to insert that cell above. Now we're in a good position to start modifying this little bit of code. I really can't wait to show you some more advanced Python programming features when it comes to functions, because Python functions are actually incredibly powerful and versatile things. And in this lesson, we're going to cover how to pass a function as an argument, how to make an argument optional by specifying a default value, and also how to have a function return multiple values. And I'm going to show you all these things by turning our gradient descent algorithm into our very own function. In fact, let's add some markdown to show this in our Python notebook. So I'm going to move this cell, this one here at the bottom. I'm going to press that up arrow here. I'm going to move this cell up, and then I'm going to convert this cell to markdown. And then I'm going to use 2 hashtags and just put down gradient descent as a Python function. There we go. Okay, let's get started. The first thing we're going to do is write our function header, as always. So it's going to be def, and then we're going to give our function a name. Let's call it gradient descent. Yeah? Followed by 2 parentheses and a colon. Now, our gradient descent function is going to be taking 4 arguments: the derivative function itself, a value for an initial guess, the learning rate, and the precision. So let's put these in as parameters between these 2 parentheses. So the first we said was the derivative function. I'm going to call this derivative underscore func, then the initial guess, comma, then a multiplier or learning rate, and then the precision. Now, if you're looking at this, then you're going to be maybe wondering about my intentions here. What do I mean by putting this derivative function as a parameter here? See, the thing about Python is that a function is actually a full-blown object. Yeah? So functions are stored in a piece of the computer's memory all on their own, just like other objects are. And this means that you can stick a function in a variable and pass functions around our program. So in our gradient descent function, this derivative underscore func parameter will be our placeholder for the actual derivative function. And you'll see this when we call this function. So now let's fill in our function body. In order to make all of these lines part of our function body, we have to indent them, because the indentation is how Python knows that these lines should be part of our function. Now, to indent a whole group of lines, what you can do is you can select them and then use a keyboard shortcut. So on Windows, you can press Control and then this key here to indent the whole group. And then on Mac, instead of Control, you simply press Command and the square bracket key. Let me show you. So I'm going to select all of these up to the break statement here, and then I'm going to press Control and then the square bracket key. And they all move over by one. So now they're all part of our function body. That's pretty neat, right? Now I'm going to modify these lines. So our new x will be equal to the initial guess that we're making here. Yeah. So the initial guess is our placeholder, and when our function gets called, we're going to supply an initial guess, and we're going to set new x equal to that initial guess. I don't need this line anymore, and I also don't need this line anymore, and I don't need this line anymore as well, because these variables will get their value when the function is being called. And I'm going to keep these around, but I'm going to have to make a modification here. Our derivative function here isn't going to be called df anymore, right? It's going to have the name of our placeholder, right? It's going to be called derivative underscore func. And the same, yeah, is going to be the case down here. This is the other occurrence where we're referring to our derivative function. So this is going to be also called derivative underscore func. I'm going to delete this comment here. Don't need this anymore. And then when it comes to graphing, there's another reference here to our previous example. But now I'm going to replace this again with derivative underscore func. I'm also going to take away this print statement. Don't need this anymore as well. And then I'm also going to delete these print statements here. We don't need these anymore as well. But there's one additional thing that I do want to add. Yeah? I'm just going to delete a couple of these lines here to tidy it up a little bit better so we can actually tell what's going on. And now I can add that last thing to our gradient descent function that I wanted to add. I'm going to add my return statement. So this is the keyword return followed by whatever the function spits out. Now, what do we want this function to return? What are the important things that we want out of our gradient descent function? We want three separate things, three separate values that we're interested in. So we want the new x value, we want the list of x values, and we want our list of slopes that we calculated, because our list of x values and our list of slope values is what we're going to be using for graphing. And obviously our minimum is going to be that new x value that we spit out. So one of the easiest ways of having a function return more than one value is simply by having our return values separated by a comma. So new x comma x list comma slope underscore list will return three values. So let's press Shift Enter now and see if we get any errors. Okay, so far so good. Now it's time to call this function. This is where the rubber meets the road, as they say, right? Now, since we have multiple return values, we can store these return values in three separate variables. So I'm going to call these variables local underscore min, comma, list underscore x, comma, deriv underscore list. Yeah? So my function is going to be returning 3 values, and these are going to be stored in this order in 3 variables. Okay? So time to call this function. Gradient underscore descent, open parentheses. Now it's time to supply those 4 arguments. So the question is, what are those going to be? So let's supply these arguments by their position. The first thing that will pass into our function is going to be, well, another function. It's going to be another function. We're going to pass in our derivative function, which is kind of crazy, right? Like we're passing in a function to another function like it's no big deal. So I already mentioned that functions are just objects in Python, just like pretty much anything else. So our derivative function is an object, and it's got the name dg. That's it. So if we want to get technical, what's in fact happening here is that we're giving our gradient descent function a pointer to our dg function that we've defined in the cell above. Now, if you've got a programming background, then you might be interested to know that what we're doing here is we're not copying our dg object. We're simply pointing to our dg object. Now let's apply our other 3 variables. Let's have our starting position be 0.5. Let's have our learning rate be 0.02. And let's have our precision to be 0.001. And let's add some print statements for good measure. Yeah, print local min occurs at, comma, local underscore min. Let's print out that first value, and let's also print out the number of steps. Yeah, so the number of steps is gonna be, well, it's gonna be the length of our list. So I can have len, so the length function of our list underscore x. So this will include the initial guess plus the number of times that the loop ran. That's going to be the number of values that are going to be stored in this list right here. Now, as a challenge, can you figure out what the problem is if I try to run this as it is? And also what I would have to fix in order for our function to run properly? Because there's something that I've missed in our gradient descent function that I've not taken into account yet. And here's the solution. So this variable here, step multiplier, yeah, exists locally within our function. So it only exists within the function itself. But the problem is that it hasn't been defined anywhere. This means that Python actually does not know what this name refers to. In short, we've got to be consistent with our naming here. So multiplier is the name of the parameter which we actually want to use. We cannot use the name step multiplier which we've defined earlier. And that's the fix. So let me press Shift Enter to rerun this cell. And now I can press Shift Enter again to run the cell below. And here's our answer. Our local minimum occurs at 1.4, and the number of steps it took to get there was 23. So our function is working. Now, looking at how we're calling this function here, gradient underscore descent, parentheses, dg 05, 0.02, 0.001 is not very readable. Yeah, this is something I really dislike when writing code, because these numbers just appear like magic numbers. Looking at this, we don't know what they mean, right? We'd have to actually know what the function definition is. It's much nicer to add keywords to these arguments. And we can do that by modifying our function call. So I'm going to take this code here, copy it, paste it down here for reference, and then I can fill in the names of these arguments. So this was our derivative underscore func. It's going to be equal to dg. Our initial underscore guess is going to be equal to, I'm going to say 0.5. And then I can actually hit enter here and go to a new line This won't affect the function call at all, but at least it's going to make our code a lot more readable. So this was our multiplier, and this was our precision. Let's see what happens when our initial guess has a starting value of negative 0.5. Let's run it now. So we can already see a difference here. So the first time, the local minimum occurs at 1.4, and the second time round, the local minimum occurs at negative 1.4. But before we investigate this, let's talk a little bit more about arguments. We already know that arguments are how a function gets its inputs. Arguments are how objects are sent to a function as an input. And I promise to show you how we can give our arguments a default value and also make some of these arguments optional. And to do that, we're going to have to modify the header in our gradient descent function, because this is where we can specify our default values. So let's specify a default value for this multiplier here. We can do that by setting it equal to 0.02. And to specify a default value for the precision, we also can just simply set it equal to 0.001. And now our gradient descent function has two required arguments, the derivative function and the initial guess, and two optional arguments. They're optional because they have default values. So let's call this function again. This time, we're only going to specify the required arguments. I'm going to copy this code here, paste it here, and I'm going to delete this part of my function call. So I'm only going to specify the derivative function and the initial guess. Now I'm going to change this guess to minus 0.1, and let's see where we end up. If you're getting this error, if you're getting gradient descent is missing two required positional arguments, despite having added this code, it's because you haven't rerun this cell. So remember to press Shift-Enter on the cell to rerun this code and make sure that our Jupyter Notebook is updated. And then come down here and run this one. And you should see that we end up at the same minimum as before, but this time it takes us 34 steps instead of 23. Now, one thing that you might try is you might want to rerun this cell here. Question is, will this still work? And the answer is yes, it will, even though we don't have to specify a value for the multiplier and the precision. We can do. So I can add an extra 0 here to the precision and make our step size even smaller by changing it from 0.02 to 0.01, and I can overwrite the default values that this function usually has. And we can see that having made the step size smaller and our cutoff point even more precise, now the number of steps increases to 56. So this is really, really cool, right? We've got really powerful capabilities with functions. We've got a very descriptive way we can call them. We've got multiple outputs that we can store in variables just separated by commas. And we can have optional arguments. So we can give default values to some of our parameters in the function when we create it. But all this stuff with arguments and optional arguments, it's kind of hidden from view, right? I mean, how would you know what the arguments are for a function that you've never seen before? Wouldn't it be nice to be able to pull up this information really quickly and really easily inside Jupyter Notebook without having to guess? Well, I got you covered. Let me show you a neat little trick in Jupyter Notebook. So if I put my cursor over my function here, gradient descent, and then I hit Shift and Tab on my keyboard, so I'm holding down the Shift key and then pressing Tab, then Jupyter Notebook will pull up a little bit of documentation, a little bit of information on this function. So I can see here, I need 4 arguments. I can see what the arguments are called: derivative func, initial guess, multiplier, precision, and I can even see what the default values are for my other 2 arguments. Isn't this really, really cool? Jupyter Notebook is actually smart enough to give us some information on our function right there and then. And it doesn't just work with our own function. So scroll up and pick out matplotlib's scatter function in this notebook and give this a try. Shift and then Tab on your keyboard. Go on. I'm going to wait for you right here. Did you try it in a couple of places? You might have noticed something. Sometimes it's really, really informative, and other times it's not. So let me show you what I mean. So I've got my Python code here from our previous example. If I go to scatter and press Shift Tab, then I get a wonderful description here with very, very detailed information on the signature. And I can click this little plus sign to even take a look at all this information here and all this documentation for our scatter function. And similarly, when I go up here to plt.figure and I press Shift Tab, again, I get a wonderful description here, a wonderful signature. These are all the things in the header. I can click the little plus sign and I get really, really descriptive information, right? Face color, the background color, if not provided, defaults to RC figure face color. Fair enough, right? Cool. Let's go to this plot functionality here, right? If I press Shift Tab on this, all I get is plt.plot and then args and kw args. So this isn't really informative, and I do have to kind of go to the documentation here and really, really figure out what it is. But it's not all that readable, right? So, I mean, you can be scrolling around here for a long time trying to make sense of all this. So at this point, you're probably much better off going to the website of the official documentation, where you can actually read up on this in a much nicer format. And you can search on this page, etc. In other words, if you want to know how something like plot or subplot works, you're probably still better off in pulling up the documentation for these things in your browser. But speaking of plots, it's time to chart our gradient descent. So let me copy the cell that generates these charts here. I'm going to go to Edit, Copy Cells, scroll all the way down, and then paste the cells above. This is our chance to play around with the starting values and our algorithm. So I'm going to add a comment here calling gradient descent function, and I'm going to edit this comment here, plotting function and derivative and scatter plot side by side. Then I'm going to take this one here, I'm going to copy it, and I'm going to paste it here. And I'm going to change our initial guess from minus 0.1 to positive 0.1. Now let's add a couple of lines of code to have that scatter plot on here as well. So it's going to be plt.scatter, and here we had our list of x values, and then our cost function g parentheses list underscore x, but we can't leave it like that because we're doing some calculations, remember? And the power function doesn't play nice with a list type. So I'm going to convert it to np.array, and then I'm going to have it inside our g function. So this is going to be the input. I'm nesting two functions here instead of splitting it out. And then we're going to add a color. I'm going to say color is red. The size of the dots will be 100 as before, and we're going to give it some transparency as well. Alpha equals 0.6. and then a closing parentheses for the scatter plot. Now, transparency looks pretty good on the other one as well. So I'm going to add alpha equals 0.8 on our cost function chart as well. And let's do something similar for our derivative chart below. So it's also going to be a scatter plot, plt.scatter, and it's going to be our list of x values again for the x-axis. And then what was previously our slope list, we've stored in a variable called deriv_list. We're going to go again with the red color for the chart. We're going to go with size 100 and alpha, I don't know, 0.5. And this sky blue line is also going to get some transparency with alpha equals 0.6. Now let's run this cell, see what happens. And voila, this is what we get. We get our initial starting value up here at 0.1, and we're descending to the minimum here. And on our derivative, it looks like this. We're going to go down, 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 until our slope is equal to 0. Okay, so let's try out a couple of different starting values for our gradient descent function in this example. So here we've started at 0.1 and we've converged to this minimum here, this right-hand minimum here. Let's see what happens when we start out with the value 2. So I'm going to say my initial guess up here is going to be the value 2. And I'm going to hit Shift Enter. In this case, our gradient descent algorithm goes down here and we end up at the very, very same minimum. And if we start out somewhere else, say like negative 1.8, then we end up at this minimum instead. We end up in the left-hand minimum. And we'll end up in this left-hand minimum as well if we start out at minus 0.1. So if we start at minus 0.1, we end up here as well. We end up in the left-hand minimum. So what we can learn from this, what we can see from this example, is that our algorithm isn't perfect. It's got some weaknesses. Because conceptually, it's a little bit disturbing, right? That we end up at completely different minima when we start out at positive 0.1 and negative 0.1. So if we're unlucky in our choice of initial starting position, we can actually end up in very, very different places. So we can see in this example that the path of the descent can be very, very much influenced by that initial guess in certain situations. Now, would you like to venture a guess what happens when we have an initial starting value of 0? So have a think about what would happen with our gradient descent if we feed in the value 0 into our initial guess before you run the algorithm. Let's try it out. So I'm going to say, instead of 0.1, I'm going to start out at 0 and press Shift Enter. What ends up happening is that we don't descend to any of the two minima here. Instead, we end up sitting right here on the maximum. And that's because the slope at this very, very point is also equal to 0. And we can see this here on the right-hand function here, on the slope of the cost function. Remember, our gradient descent algorithm stops running once the slope is equal to 0. So this problem is also related to the sensitivity to the starting position, right? The sensitivity of the path of the gradient descent algorithm to that initial guess. Now, in this case, both of the two minima have the same cost, right? The cost is equal at both of these two minima. But we can also imagine a very different situation. If our cost function looked something like this, then we would have two minima, one of which has a much lower cost than the other one. One of these is a global minimum, and the other one is a local minimum. So the local minimum actually has a higher cost than the global minimum, but our gradient descent would not discover the global minimum if the initial starting point was on the right-hand side of that local maximum, of that small hump right there in the middle of the chart. Okay, so we've outlined the problem. What's the solution, right? How do we get around this weakness? Well, the easiest thing to do would be to simply try out multiple different starting values and see if they end up in the same place. Think of this as like injecting a little bit of randomness into our gradient descent. So we could do this by choosing a whole host of like random starting values and then running our gradient descent over and over again to see where it ends up. And this might be an approach you could take if you actually don't know what the cost function looks like, right? If you don't know where the minimum is, this might be something that you'd want to try. Another thing we could do is to try a completely different algorithm to find the minimum, right? Because let's face it, this particular version of gradient descent isn't our only option. Similar to how we can try a bunch of different random starting points, other algorithms have randomness baked into them. One of the versions of gradient descent that has more randomness baked in is called stochastic gradient descent. And this is in contrast to what we're currently doing, which is called batch gradient descent. But the thing to note about any of these approaches is that none of them are perfect, right? You'll find that no matter which approach you choose, it has certain strengths and it has certain weaknesses. And it's important to understand what the pros and cons are of each approach. So on that note, we're not done yet examining this particular algorithm. Our batch gradient descent algorithm might actually face another problem. And this is what we're going to be looking at next. I'll see you in the next lesson. Take care.